So far we've been talking about model problems, the advection diffusion equation and the Stokes equation. So now let's try and take a few steps forward and tackle the problem that we actually mean to address, and that's the Navier-Stokes equation. So I've repeated the Navier-Stokes equation here. Feel free to rewatch the lecture on the Navier-Stokes equation. I think it's one of the first lectures that I recorded in the series. And let's try and solve this with a numerical method. Now, what would that mean? First of all, numerical methods are about solving linear systems of equations. And this is a nonlinear partial differential equation. So how would we go about solving something like that? Well, if you've taken classes in finite element analysis, then we know that if we have nonlinear problems, then we iterate to solutions. And there are different iteration schemes, for example, Newton-Raphson scheme. And within each iteration of a solution step, we linearize our nonlinear equation. So if we're trying to solve the Navier-Stokes equation, well, what we should actually be trying to answer is whether we can solve for a linearized version of these equations. And once we can solve for a linearized version of these equations, then we can solve for iterations of these linearizations of these equations to iterate to a solution of the nonlinear equation. So our nonlinearity occurred here. And the linearization strategy that I'll propose and that I think is sufficient for understanding the points that I want to make is to simply replace u by a function independent of u. And once we then can solve that system of equations for any choice of velocity, and then that means that we can perform each iteration. So let's first consider a rewrite of the Navier-Stokes equations that has the following linearization assumption. So we still have our time derivative, but now I'm replacing this first u by some vector field beta. And of course our second equation is still divergence of u is 0. Okay, so is this what we would try and solve with a numerical method? Well, not entirely yet. Typically, once we deal with time derivatives, even though we might be solving the complete system of equations with, for instance, a finite element scheme, you would still treat the time derivative with some form of finite difference scheme. And if we treat the time derivative here with some form of finite difference scheme, then we take the previous, in some sense we take previous solutions and current solutions, and we take ratios between those, and the previous solutions end up in the right hand side, and then the solution for the new time step still ends up in the left hand side. So in whatever form, but you would get something that has simply a weighting by let's just call it sigma of my current solution plus, and then still all my other terms. So just to make this a little bit more clear, sigma would be, for instance, 1 over dt if you take a backwards Euler time differentiation. So finite difference treatment of the time derivative. So then we get yet another more simplified version of our Navier-Stokes equation that is actually very relevant to us because, again, that's precisely what we're trying to solve for if we're designing a numerical method for solving our fluid flow. And these simplified versions, or this simplified version of the Navier-Stokes equation actually has a different name. This is the Oseen equation. Well, these are the Oseen equations. There are two equations, momentum equation and an incompressibility constraint. These are the Oseen equations. So the way that I'm going to interpret the Oseen equations are or is a linearized steady the Oseen equations are linearized steady Navier-Stokes equations with a reactive term. Right? This term is a reactive term. And that is in fact precisely what we need to be able to solve in each Newton iteration, or in each time step, or each Newton iteration of each time step. In our finite element code. So now there are different facets to the analysis of how these equations are going to behave. One part would be how is it going to evolve in time. So given a certain finite difference time discretization, and suppose that I can solve this equation for each iteration in a Newton algorithm, and suppose that that converges, then still how does that advance in time? Does that blow up? Does it diffuse? So we have a certain transient behavior that might be interesting to the stability of, to understanding the stability of the partial differential equation and the stability of the numerical method. Now the second thing is precisely that Newton iteration. Even though I might be able to solve each iteration independently, does that converge to one solution? So that's also has to do with the stability of the nonlinearity in a sense. So, and then thirdly, we have to question whether we can actually solve for each iteration in our Newton scheme for any given time step, which comes down to being able to solve precisely this linear system of equations for any particular choice of beta. And that is what we'll focus on in this short lecture series. Yeah? So the stability analysis that we'll talk about is whether or not we can actually solve for any single one of the iterations in a Newton set of Newton iterations to handle the nonlinear term within one time step of a series of time steps. Yeah? Because if we can't do that, then we can't do any one of the subsequent steps. So the relevant question that we are concerned with for this part of the analysis is whether the finite element formulation of an Oseen equation permits a unique solution. So that means that we have to dissect our Oseen equations in the different segments that we are familiar with. Now, first of all, what I'll do is first of all, we'll look at the terms that we actually know. So this part of our Oseen equation is the part that we've just discussed quite extensively for a series of videos. This is the Stokes part. And we know that the stability analysis of that is quite sensitive. Yeah, we had these different element types, and we want to have stable types, stable pairs. This part of the equation is the advective part. And from our previous videos, we know that also that is quite sensitive. If we have a very large beta, then we get these advective instabilities. And then lastly, this part is simply a reactive part. Now that again is due to the time stepping. In general, reactive parts of an equation are coercive, right? If I multiply this by a test function, then well, that's going to be a square term. So typically, these contribute to the coercivity of our weak statement. This is the mass matrix, or at least an L2 mass matrix. So that adds coercivity, and in principle, we're happy with this term. Now, nevertheless, I don't want to have to rely on this term. Yeah, so in my stability analysis, I don't want to get results that I will only be stable if I can rely on sufficient small or large time step. That you might have such relations for having stability in time. Well, that's another matter. But within one iteration of one Newton step, I don't want to have to assume a certain contribution of my mass matrix in order to have a solvable system. Yeah, so the analysis that we'll actually perform is a combination of the blue and the green box. I want to make sure that the weak formulation corresponding to the blue and the green box together form a solvable discrete set of equations. So, in summary, we don't want to rely on sigma for being able to solve one iteration of our Newton algorithm. So first, proceed with sigma is equal to 0. And every other sigma is then going to improve our results in terms of our coercivity constants or whatnot. So let's proceed with sigma is equal to 0. So we're killing the reactive term here. We only have the advective and the Stokes terms left. And let's produce a weak formulation for that remaining problem. Well, again, we have a solution field that comprises of a velocity field and a pressure field. So our weak statement is going to be that we're trying to find a vector field U and a pressure field P in, well, again, H1D, the dimensionality of our geometry, cross L2, such that, well, for all test functions V, yeah, I'll write that here, such that for all test functions V, Q in the same spaces, H1, and again, let me assume 0 boundary conditions here, we've discussed this before, times L2. We have the following two statements. Firstly, we have beta dot gradient of U, comma gradient, comma V, L2 inner product between these two, plus nu times symmetric gradient of U, comma symmetric gradient of V. Now that's the term that we also derived in our Stokes equation, for our Stokes equation. Then we have minus P times the divergence of V. That's going to be equal to the L2 inner product between F and V. And our second equation, of course, gives the same expression. Now we can either multiply that by -1 or not. If you multiply it by -1, then we get a symmetric system of equations. So let's do that. And then you get Q divergence of U is equal to 0. So this is a weak statement of our Oseen equation, in the sense that it's just a combination of an advective term, an addition of an advective term to our Stokes equation. Yeah, so the analysis of these equations are pretty much going to be a sum of those two analyses, stability of the advective term plus stable element pair. But as I said towards the end of the last video, we're actually not quite so happy with being constrained by our choice of elements. And if you can use an element for which you're absolutely sure that it is stable, then that's probably what you want to do. But there might be some cases where you don't have this luxury, or you have to make a different choice for some reason. And then we get to the field of pressure stabilization. So a couple of reasons of why we might want to use element pairs that are not stable are, so suppose that we don't want or can't use stable pairs. Okay, and the reasons for those might be, for example, the following. We want to be able to use low element pairs. Yeah, so we know that this is not a stable element, but maybe we only implemented linear basis functions, or this is we're extending from a finite element code for solids, and that's where we have these basis functions implemented. Or in general, this is typically the first set of basis functions that you would try. It's the most natural choice. Or extending on that, we might want to have something that has optimal convergence in both U and P for equal order pairs. Yeah, remember that our error analysis for mixed problems was that we can only say something about the sum of these errors measured in very specific norms, right? H1, and that was bound by some constant times h times the minimum of the polynomial orders, but the difference between PU and PP. I suppose that we want to use equal order interpolation for U and P, such that, well, this would be one of the examples thereof, right? P1, P1. But we want to be optimal both in terms of U and in terms of P. Well, given this in sub condition and this limit of our or this upper bound of our error, we're essentially throwing away a whole bunch of degrees of freedom that don't contribute, because if you have equal order interpolation, for instance 2, 2, then you would get the degrees of freedom for the pressure don't contribute, right? We're taking the minimum here. So you would get a value 2 as opposed to 3. So you wouldn't get the optimal convergence for your pressure anymore. Yeah, so suppose that you do want to use equal order interpolation pairs, and you want to get good error convergence for both fields, then the theory that we discussed so far doesn't quite cover those bases. Now, another good reason why you might want to use elements that are not stable is because you want to use R2 pairs. Nope. Yeah, where R is our constraint ratio. Remember that our stable pair, the Taylor-Hood element, had a constraint ratio of 8. And even though that had optimal convergence, the solution fields for the velocity did not quite satisfy our incompressibility constraint very well. And suppose that you're dealing with problems where that incompressibility constraint is actually very important, you don't want to have any mass loss, then it's important that we use pairs that are very close to this R2, this ratio of 2. And that's again specific for the two-dimensional case, so let me say actually R is equal to D, right? The physical dimension. Now we had some examples of R is equal to D case elements. and those were the ones that had these spurious oscillations for our pressure field. So supposedly you do want to use these because you know that for the velocity field they actually give quite good results. Yeah? So then we have to somehow perform some tricks to stabilize our pressure field. And well, the last one is actually pretty straightforward argument. In general, I just want to be flexible. I just want to be able to use my finite element scheme for whatever choices of elements that I want to make, and I want it to behave properly. So I don't want to be constrained by having to do all kinds of analysis to see if my element pairs are stable. So if we run into any one of these four cases, and I'm sure you can find more arguments, then we're not happy with the conclusions that we drew in the last couple of videos, and instead we would want to do something else. We would want to introduce pressure stabilization. Yeah, so these are stabilized methods in the same way as the stabilized methods for the advective term. So we're adding additional terms to our weak formulation. And we're doing this in a smart way, in such a way that we circumvent the LBB condition. So that's actually a terminology or a phrase that you'll find often in literature on this topic, that where the pressure stabilization circumvents the LBB conditions. Now, what does this look like? This means that we're actually going to introduce a series of different types of stabilized methods. So let's consider our system of equations. If we have our velocity degrees of freedom and our pressure degrees of freedom. And as we know from our analysis of the Stokes equation, that actually normally gives us a bit of a saddle point problem. Where normally the bottom right corner is 0. Then on the bottom, or the top right and the bottom left corner, we had these divergence terms, and that's exactly the terms that we've been analyzing for a couple of videos. And this term would end up in the upper left corner. Now for the Oseen equation, we have one more term. This is a term u of v, so that fits in the same box as this term u and v. So that really only gets added over here. Yeah. So in that sense, we're dealing with the same type of problem. We have a matrix of the form A, B, B, T, 0, right? And that's the saddle point matrix, and that means that we have to go through all the steps of the previous videos. So introduce. So at this point, when we're making use of this weak formulation, we are at the point where we're not happy. Yeah, so now we want to do we want to make some changes such that we're not constrained by these choices of stable element pairs. What we're going to do is we're going to add different stabilization techniques in this matrix. Well, the first one, to kind of illustrate the point that I'm trying to make here, let's first talk about the SUPG method. That's the one that we already discussed before. That was the one that we need for stabilization of our advective term. What does SUPG look like again? Well, we have a residual, and I'll get back to this in a second, times, well, actually a stabilization parameter tau times our advective term, but now on the test function. So we have beta dot gradient of v. So this is the term that we're adding. That's SUPG. And depending on how you define the residual, there would actually have to be a minus up front here. So now we have two equations. What residual are we talking about here? Well, we're talking about the residual of the momentum equation. Yeah, because we wanted to have this cross term in there, the advective term times the advective term, that ended up being a diffusive term. Yeah, so the residual that we're talking about here is the residual of the momentum equation. Yeah, so I'll write it as Rm, which is vector valued, right? So if you subtract maybe I should look at the strong form equations here. If you subtract if you subtract the left hand side from the right hand side, you obtain a vector expression. So we have a vector dotted with vector dot gradient of a vector. So this is a second order tensor. Dotted with a vector gives a vector. So we indeed have to multiply it again by a vector to get a scalar. Now, where in our matrix system of equations does this actually show up? These SUPG additional terms of our SUPG integration. Well, first of all, we have our test function on the velocity. So that's this set of equations. These are the ones that correspond to the velocity test function. So SUPG is going to fill the upper part of our matrix. Then we're multiplying that by the residual of the momentum equation. Which degrees of freedom show up in the residual of the momentum equation? Well, actually all of them. We have our velocities, but also our pressures. Yeah, so in our matrix system of equation, SUPG is going to have impact on this submatrix, but also on this submatrix. And we can already see why stabilized methods kind of changed the analysis that we had to do, because in all of the previous videos on the mixed methods, we were very concerned about the properties of this B matrix that had to be full rank, and now we're adding terms that are changing these matrices. And we're hoping that these change these matrices for the better. So, now that's not all we're going to do. We're going to add two more stabilized methods. We're going to add PSPG, pressure stabilized Petrov-Galerkin, and I'll actually talk about that one in the next video. But for now, I want to illustrate where these are going to affect our stiffness matrix. So that's going to be pressure stabilized Petrov-Galerkin. Nope. True. Pressure stabilized Petrov-Galerkin. This is actually going to be a method very similar to SUPG, but we have a different term on the right lid. We will actually have a term that involves the pressure test function, Q, and as a result we would get terms that affect these submatrices, PSPG, PSPG. And then we'll use one more stabilized method, and that is the least squares on the incompressibility constraint. Oh. Compressibility constraint. And that is only going to affect this block. Okay, and we're gonna go into a little bit more depth on well, each one of these stabilized methods for this week formulation. Specifically, we're gonna go into more depth on the PSPG and LSIC methods. But what I want to illustrate already in this sort of introductory video is how these stabilized methods affect this matrix. Namely, we have these additional terms that just change the values in these different submatrices. And the important thing to realize is that they change the B matrices. Those are the ones that we had to analyze. And they fill this lower right corner. And if we do not add PSPG, pressure stabilized Petrov-Galerkin, then that lower right corner was filled with zeros. And because it was filled with zeros, this corresponds to a cell point problem. There was a constraint in there. And that is precisely what gave us all the headaches, actually. It was precisely that zero block. Because in that case, if there's a zero block over there, then it's very straightforward to show that our system of equations is not coercive, right? That was pretty much what we started off with. We said Stokes' weak formulation is not coercive. That's why we have to go through all these hoops. If we add these stabilized methods, then we affect our discrete system of equations. We add a whole bunch of additional values to our matrix, specifically also in this zero block. And because of that, we can actually rely again on our coercivity analysis. And that is something that we like, because if you can prove coercivity then that typically has a more general impact on our finite element approximation. If you can prove it for the continuous case of infinite dimensional spaces, then it also holds for each one, every choice of refinement of your finite element subspace. Yeah, so I think that the thing that I want to conclude with in this video is that our stabilized methods are going to be consistent filling of the stiffness matrix, specifically of the saddle point stiffness matrix, such that coercivity is retrieved. And if coercivity is retrieved, we no longer require inf sub or LBB conditions. So we no longer require analysis of, I should say. Yeah, and because of that, we are much more free in our choice of finite element spaces, and we can consider each one of these cases. So I think there will be about 2 or 3 more videos on the topic of pressure stabilization, 1 or 2 of which I'm going to discuss these different stabilization techniques, and then the last one I'll actually talk about the stabilization parameter, tau. So far I've tried to kind of avoid the discussion in this direction, but I think at this point we're ready to talk about that. Okay, that's it for this one. Thank you for your attention.